Vineet Tyagi. He has been a project associate for the project we've been working on. He's going to talk on digital twin for real-time detection of leakages in water pipeline networks. Vineet Tyagi, like I said, has been a project associate with us at IISc for last 2 years on this Indo-Dutch project. Prior to that, he had been working in various analytics profile in wealth management and business consulting. He has a BTech and master's degree in metallurgical engineering from IIT Bombay. Vineet.
Thanks, Shashi.
Yeah.
So I'll start sharing with my screen. Let me know if that works fine. So
yeah, we can see your screen, Vineet.
Yeah. Yeah. Is it like full page, or do I need to make it full page?
It's not full screen. So if you want, you can make it into a slideshow.
Yeah.
Yeah, Vineet, in the bottom right, I think there will be something which lets you make it full screen.
Yeah, I think this. Now it's better. Yeah.
Yeah.
Yeah. Yeah. So, hi everyone. So, in this work that I'm going to present, we are trying to solve a real-world problem where where digital models can be used to monitor water distribution networks, and in general, it's yeah, it's now the next slide. Yeah. So in general, I mean, it's and models like these are in place, and what we are trying to do in this exercise is try to create models which are based on machine learning. Before we go there, we'll just see what exactly we mean when we say a digital twin for water distribution network, where we can simulate WDNs or water distribution network. So typically, in the labs, people have well-established empirical relationships that try to understand the flow of water or in general fluids in pipes. A lot of models use these empirical physical relationships, and they try to model the actual setup and trying to predict the expected behavior. But these models, they require a lot of details about the layout, about the physical infrastructure, which includes the pipe, the shapes, the friction in the pipe, the material, etc. And then the way these models would work would be that given this information about the network, they will use the empirical relationships. Just for explanation's sake, I've mentioned this in a very simple form. Essentially, these equations will play around conserving mass and energy, and they will be solved algebraically to predict pressure and flow in the various parts of the network. In fact, for all these exercises, we have used a model like this, which goes by the name EPANET, to generate synthetic data. We'll come to that later. But what we also realize is that although there are advantages that these models are very understandable and they are easy to interpret. At the same time, they can detect any deviation from expected behavior in real time. But what we do realize is that implementation of such models can be tricky. because when you go in real world setup where the particularly water distribution networks can be very large, spread over a large area, and a lot of information, which is like critical information may not be available. One such information would be demand. We typically, there won't be any control um, uh, over how much water is being drawn by, say, individual users for household use, in fact for industrial use also. There may be an approximate range, but these models, they don't rely on approximation. They need exact data, the demand is. So those things we realize are critical, and they may kind of it may not be, and sometimes you will not be able to use these models if the information is not available. So that's why there's a case for using alternate ways. And given that all these distribution networks, they have a number of sensors in place which will at least monitor pressure and flow, and this data is collected typically at a rate of every 15 minutes or so. A lot of data is available, which typically is not used that well. So we thought that why not think of a way in which we can use this data. Here in the approach that we're going to discuss, we, instead of, say, finding out or calculating pressure at a point or flow at a point, for reasons which will become obvious with the presentation, we chose to predict pressure drop between any 2 points where the measurements are being taken, given the flow in the vicinity. So there are certain assumptions where we assume that there are places where in the close vicinity, or best case at the same point, we are measuring the flow and pressure. And for example, just to explain this point with a graph in graph. Suppose we chose a small part of the network where we are trying to learn what is the pressure drop between, say, node 28 and 29. This is one of the corners in the network I had shown earlier. What we realize is that the model, a very basic model, can learn the pressure drop between these two nodes, which are basically joined by a single pipe. There's nothing in between. If we know what is coming into this node and what is going out of this node, when we say node, you can just assume that there's a place where water is being taken out, and at the same time measurements are being taken for the pressure and also for the demand of water. So if we have this full information, in a way, it's sort of expected that in a basic linear regression model, will be able to learn it well, which is the case. We see a pretty good classical fit. But if the information about how much water actually is being used or being taken out of the system at these two nodes, basically we don't know what the demand is. What we realize is that even for this very simple case where we are talking about a single pipe, we can only approximate what would be the pressure drop given what is flowing in and what is flowing out. This again is to some extent intuitive, that with the lack of information which is required to explain the system, you can only approximate. But this work revolves around living with this error. And before we move there, we also tried some experiment again with the synthetic data, where we said, okay, if it is not a single pipe, instead of that, if we are talking about, say, let me call it a subnetwork, where I have some readings in at one spot and some reading in another spot, I don't know what's going on in this whole subnetwork. Can I still learn the pressure drop say node here, node 26 and node 20, given the flows in the vicinity, here I've taken flow 23 and 26 is known. Again, we realize that, if we know how much water is being taken out, which is the demand information, we don't need any other information. We don't need information about what is the length of the pipe, or what is the what are the properties, or what is the friction. All we need is historical data where we can train a basic regression model, and it will do the job. And again, without demand information, we will not be able to make good predictions. I mean, we'll have to live with error. For that matter, we also tried not very deep but neural networks, which and thinking if they could do the job, and we got more or less the same results. So accuracy didn't improve much. So here we come to one part of it where we are saying that, okay, if we are using basic machine learning models, or to that matter little more complicated models, will we be able to learn pressure drop between any two nodes, which we choose as a parameter to predict or to monitor when we talk digital twin in this case? And what we realize is it won't, I mean, we will not be able to get good accuracy. We'll have to live with error. And more than that, I mean, more importantly, these models which are approximating, they will not be able to tell if the system has changed, if there's an anomaly, or maybe there's a theft going on, there's a leak in the system, and the underlying conditions have changed, because we are still living with a lot of uncertainty. So from there, while working on the problem statement, we thought of an alternate approach where we said, okay, let's look into the error because it contains some information. Let's look into the error a little more deeply and see if we can infer more than it looks, or intuitively someone may think. So the idea here is that, and also the approach is closer to reality, where you will have sensors only at few places, and you have only limited data about the whole network. So suppose we assume that in this network, where there are like close to 32 nodes and 34 links, we have sensors in 7 places. So it's decently decent amount of sensors, but not like heavily censored. And then from there we say, okay, we will start monitoring pressure drops, and we'll use the term delta H between any pair or any sensor pair. So for example, 1, 2, 1, 0, whatever. We'll try to learn the pressure drop between, say, in these two sensor cases, between node 4 and node 9, given the information which is flow in link 4 and 9. So that's the way we structured our problem, or our experiments. As expected, as we had seen earlier, just for illustration purposes, we took 2 sensor pairs, and then we saw that we got similar kind of results, where there is an error when we try to learn delta H given the flows. But the underlying thought which we are presenting today is that this error for any given sensor pair should remain similar over time if the underlying parameters which are driving the whole flow doesn't change. So we are saying that you are talking about similar kind of demands every day, let it be industry, let it be household. We are talking about similar kind of pressure being maintained at the source. So whatever is expected, and on a daily basis, what's happening in our distribution network, it continues. Then on an everyday basis, our model will predict pressure drops between these sensor pairs with an inaccuracy, but the inaccuracy itself should have a pattern. And that's where we say that if there is an anomaly, if suppose there is a leak or there is a theft, we expect this error profile to change. So with that, we did certain experiments. Again, these are all using the software. And anyways, I mean, if you want to model leaks, I mean, it's not really feasible to use a real network. So you'll have either an experimental setup or a software. So here what we observed is the blues are the one where the network is without a leak. And in this case, we had introduced leak in one of the links. When the leak is introduced, and the same sensors, so data from the same sensors is being monitored, we see there is a shift in over a time. The observations that you make, there's a shift from what you have been say observing in past, and when we say in past, we're saying that the scenario where there was no leak. And this shift is also visible when we try, when we plot the error in the prediction. So this error essentially is that you have delta H, which is observed from the sensor data, and then it is predicted using a linear regression model. And there is a difference between these. So there's the error, but the error profile changes when there is a leak. So and we also see that there's a shift in the mean, and there is also a slight change in the shape. And we'll later on see that we will use these statistical properties of these two profiles to further this work. And we also see that the impact on say one sensor pair versus another sensor pair is different for the same leak. So these ideas are basically the driving ideas, where we say that a change in the error profile indicates presence of an anomaly. We have used the word leak. It could be theft or whatever, but there is a change in the underlying conditions. The extent of the change, that will depend on the relative locations of the sensors in the leak. And this fact or this observation is used later on to identify where the leak is present. Again, just to mention that we have used Ethernet to generate data with and without leak. And the setup that we have used, we have assumed 7 sensor locations. We have leaks one at a time. So here another important point is that we are talking about one leak. Essentially, we are saying that we are trying to tackle the problem in incremental leak. So of course, there can be at the same day there can be leaks in 5 places, but right now the problem statement is confined to one leak at a time. But for training purposes, we have introduced leaks in 3 locations, one at a time, to generate data. So here the way the structure works is that we have like 2 layered solution, where the first layer is a regression model, and this regression model essentially learns to approximate pressure drop between any 2 sensor pairs. And this model essentially gives us what we call the predicted delta H, and we have an observed delta H. So the predicted delta H is where this is the model which we use. Once the model is trained using some data, and this data is the data that in real life we will say is data without leak. I mean, of course, it can happen that in an existing network you're living with like leak in 5 places. But whenever you start, you say that my historical data is what I live with, and what I assume is my status quo. so that we are using the word data without leak. Uh, uh, then with this model in place, we go to the next step. The next step is where we say that we have a reference data. Now, in real life, the reference data could be that, if somebody is using this model to monitor a distribution network, and he has data for, say, last 3 months, or could be like last 4 weeks, etc. These are the things which will work on next stage. And we said, okay, this data is my reference data, and whatever is my error profile in this length, in this time period, is what I expect to continue. At the same time, there is another data which we say is again coming from the sensors. We call observed data, which is, say, last. I mean, these are, I'm giving these examples just to bring home the point. It's not necessarily exactly what we plan to do. Another set of data could be, say, last 1 week, which is the recent data where we want to check that if something different has happened in this near history. We take these two data sets, we take them to the regression model, and then we have two set of prediction errors. So one prediction error is, we say that an expected prediction error, and another prediction error is, we say it's an observed prediction error, which could be recent, based on recent data. And when we have these two error profiles, as we had seen in the charts earlier, we put them together and then we compare them. We compare them for similarity. And for these experiments, what we have done is, for these two error profiles, we have compared their means, or not compared actually, we have just stored their means. And we have also done a similarity test. The one that we have used is the Kolmogorov-Smirnov test, or the KS test. And we have stored the KS statistics. So this we have done for all the possible sensor pairs. And then with that data in place, for the training purposes, we also had a label, because this observed data is the labeled data as far as the training goes, and also the experimental testing goes. So along with these these features and the label, we prepare a we can do a classification model, which we can now train to learn the leak was there. The leak was there, in case it was there, where it was, in those 3 locations that we chose. Based as a models that we have used for regression, we used a linear regression model, and they were doing a job good enough. And then we also used tree models, but then when we tried logistic regression, it was giving more or less the same results, and much faster. So so far we have been using only the simplest of the models, the linear regression and logistic regression. And based on that, the results that we got are fairly encouraging, at least for the engineered data. And as we can see that, when the data is clean, then we are able to identify this case where we say the class 0 is where there is no leak. And the 3 locations that we chose for experiments, we could identify them with very high accuracy, in this case 100%. But even if we randomly choose some other data, it was always close to 100%. We also we experimented with adding the noise to whatever data we had. Even with noise added, the results were fairly good, and there was, of course, some mismatch. But what we realized is that this approach conceptually looks good enough to at least try on the real data, which actually is the next step, where at IISc there is a network which uses recycled water for most of the time irrigation purposes. And this, right now we are in the process of putting in sensors at the locations we desire. And then with the data from those sensors will be used. This method that we thought may work, and this method we discussed, we'll try to use it with the real data. So this is currently the plan and currently where we stand. So I think that's all. And now we can take questions if people have.
Thank you, Vineet, for a very nice talk. We are slightly off the schedule, but yeah, well enough. Questions for Vineet, you can kindly type it in the chat window and then I will pass it on. So, Vineet, this noise that you had in the last slide, what was the noise that you were talking about? Or how do we interpret that noise?
So basically, the way when we install a sensor, those things, they come with the specification. So there generally they say that, okay, whatever the reading is, they have been calibrated within 1% error. So here we have used 5% error, saying that, okay, sensors may not be very accurate, and if the real pressure or flow is say 10, they could be off by 5%. So that's how we start randomly added noise within the 5% range, basically limited by 5% range. So it could be 1%, 2%, but till 5%. So that
Okay,
kind of
yeah.
data.
So there's a question from Case. What problems do you expect extra when dealing with realistic network? So yeah, when we move to the IISc network, maybe some problems that you foresee?
I mean, frankly, there can be numerous ones, but some of them could be, for example, here we have assumed that at the exactly same spot we have pressure and velocity or the flow rate being measured. If they are little off the mark, that could be one problem. And another problem, of course, could be noise. Of course, we tried dealing it with by adding noise in the generated data, but I think the noise that we'll have in the real data could be a different source. It necessarily is not just because of issues with the sensor. So we'll have to see. And yeah, I think one problem which could I shouldn't say derail, but it can be a big challenge, would be the transient nature of the actual flow. So here we are talking about steady state flow. And so all the results that we have are essentially when the flow is stabilized. But in actual practice, there will be people who will be running off the wall, on the walls, the flow in the pipes, it's not like it's a steady state of full flow. So when we are looking at the sensor reading, I don't know, I mean, we'll have to either differentiate between a transient reading or a steady state reading, or we'll have to build in the model, we have to build in capability to handle transient flow.
And also I can imagine that the leak might not be where you expect it to be, right? So it could, in the simulation, we had leaks only at a specific point.
That's another important point. Yeah, so here, in fact, I should have mentioned, when we say leak, essentially you're talking about a link. So if there is a pipe which is 2 kilometers long, right now for the model, we could nicely choose the middle point, which is a center point, and say that, okay, this is where the leak is. But the reality is, even if the leak and the model predicts where the link in which the leak is. Now, if my pipe is 2 kilometers long and my model is predicting that, there is leak in this pipe, it may not be very useful information. I mean, it's still useful, but not very useful for the people who are trying to fix it. The model, the pipe could be 10 kilometers long. So that is another thing where we need to work more, that once you have identified where in which link the model is predicting the leak, maybe we can another step or maybe another model. If the data is available, we can identify, we can move closer to the area where the leak exactly is.
Okay. If there are no further questions, I thank Vineet and the other speakers for the very nice first session.